Among other things, soil is a mixture of small mineral particles, which we call sand, silt, and clay, according to their size. All these particles have come from the great variety of rocks in the crust of the earth. Rocks which we only seem to notice in mountain districts or on the seashore, or where man has laid them bare. Rocks such as the limestones and granites, the sandstones, shales, and a host of others. Granite, one of the rocks called igneous from its origin in the bowels of the earth, is a mass of minerals in crystal form. In a broken piece of granite, these crystals can easily be seen. Some are quite large, some small. Many have distinctive colors. Others can only be identified under the microscope. Of these minerals, quartz and the feldspars are perhaps the most important. For the hard quartz crystals make up the bulk of most sandy soils, and the softer feldspars, after a long period of breaking up and chemical change, end as clay soils. Sedimentary rocks, of which this limestone scarp is a good example, are very different in character and origin from granite. They are made from the broken down remains of older rocks which were deposited on the beds of prehistoric seas or lakes, later emerging again above the level of the waters. Most of Britain is covered by such sedimentary rocks. Sandstone is a common rock of this type. Under the microscope, it is seen to be made of worn quartz crystals cemented together. It is these worn crystals which are separated from one another by the weathering of the rocks, and which form the basis of a sandy soil. Many of the sedimentary rocks are made of other materials. This great cliff was built of layer upon layer of limy seashells. Here, these relics of bygone life are quite large and easily recognizable. Others are microscopic in size. Many creatures of the sea played their part in building massive rock formations. One creature, the tiny Globigerina, is found in the sea today. Yet millions of years ago, countless myriads of its shells sinking to the bottom of a primeval ocean built up the vast deposits which we know as the White Cliffs of Dover. Maps have been made in which each kind of rock is shown in a different color. We can compare these with maps showing the broad general types of agricultural land and see how closely they are related. Here, for instance, in the Weald of Kent, the agricultural character of the land, shown on this map, follows closely the pattern of the rocks in the geological map. Or here in the north of England, the marls and sandstones of the Eden Valley match exactly the pattern of fertile and productive lands beside the river. In some lands, particularly the hot desert mountain countries, wide differences between the heat of day and the cold of night cause expansion and contraction in the materials of a rock. This force can break up rock, resulting in a type of weathering called onion skin. This sometimes happened here in the distant past, but today, in our present mild climate, it plays only a very minor part. Today, the greatest agent of weathering is water. Water was responsible for the building of the great heaps of rock litter seen in mountain districts and is still adding to them. It runs into every crack and crevice, and when it freezes, the ice expands and forces the rock apart, widening the cracks. In time, pieces break off and fall to the foot of the slope. But there are other ways in which water plays a part in rock weathering. When water comes in contact with some rock minerals, like this calcium sulfate, it alters them chemically and changes the size and shape of their fragments. And so the rock of which they are a part begins to weather away. Here, for example, are crystals of the mineral olivine, which under the influence of water have been partly changed into a quite different substance, serpentine. Many rock minerals dissolve in water or in weak acids, and the more soluble parts of rock begin to crumble away. The grikes of the Pennine limestone are a good example of the result of this action. Water in the form of glacier ice is another force at work in weathering. Today there are no glaciers in Britain, but 25,000 years ago, glaciers covered much of the country, and their effects on our soil and scenery are still with us. These ancient glaciers tore away parts of the underlying rocks and smoothed the surfaces. This produced the typical U-shaped valleys so common in this country, especially in the north. Smooth rocks, scored and polished by the passage of the ice, are another sign of the glaciers of the past. Rock debris scored out from the bed of the valley, together with material which has fallen from above, is carried along by the glacier ice stream, sometimes for great distances, and deposited elsewhere when the glacier melts. Many boulders, erratics they are called, scattered about the country, testify to this, for some of them have traveled on glaciers to their present resting place. But more important in soil making are the vast quantities of smaller rubble and grit carried by the ice stream and left in heaps called moraines. We can still see remains of these in our mountain valleys today. In other places, glacial action left thick deposits called boulder clay. These surface drifts cover wide areas of the country and greatly influence our present-day methods of farming. During the ice ages, the glaciers spread over most of the country as far south as Hertfordshire. Sometimes valleys were blocked by the ice and large lakes were formed. This happened in the Vale of Pickering in Yorkshire. In a lake such as this, the mud and stones from the melting ice settled on the bottom. When the ice dam burst, water and debris spread over the countryside below. Elsewhere, wind has played a part in soil making. In the ancient past, this country went through a stage of dry desert conditions. Fine rock material was blown about and collected as sand drifts. Today, wind erosion only takes place locally, notably in parts of East Anglia, where loss of soil occurs every year, often damaging crops. Here are grass roots from which the soil has been scoured away by the wind. It was desert wind-blown material which made up a part of the new red sandstone formations, have in the course of ages been washed away by rivers and settled elsewhere. The buff and orange areas on the geological map show the extent of these formations, which cover a large part of the country. The farmer benefits today from fertile soil made from these drifting materials carried by ice or wind or water. But of these agencies, water is by far the most important. It operates continuously, laying down the raw materials for the soils of tomorrow. Rock fragments which break away from mountain crags fall down the slopes until stopped by heaps of similar fragments. The squeeze of waste water are one of the finest examples of such a deposit. In time, the rock debris reaches a valley and is swept along by a stream. It scours out the stream bed, widening and deepening the valley. The V-shaped valleys carved out by streams are quite different in appearance from the U-shaped valleys scoured out by ice. A young river in spate can move large boulders, and the grinding of boulder on boulder makes them smooth and round and wears them away. When the stream reaches a flat valley floor, the flow of the water slows down and part of the load is dropped. First, the larger stones are left behind, forming shingle banks along the stream. These become the valley gravels, which eventually make poor, low-grade soil. Often terraces of valley gravel can be seen high above the present bed of the river. On the River Findhorn in Scotland, 14 levels can be distinguished, marking the different heights of the river many thousands of years ago. Many of these river terraces can support cultivation. When the river enters a lake, its speed is checked still more, and fine alluvial deposits settle. These may become extremely fertile soil. The coarser silt is dropped first and forms a delta. The finer particles are swept on and out into the calmer water, where they fall to the bottom of the lake. The Weald of Kent and Sussex lies on lake deposits of this kind, laid down many millions of years ago. As the river reaches flatter country on its way to the sea, its flow becomes still more sluggish and it meanders in its course. In such places, there is usually an extensive floodplain. This is sometimes very fertile, sometimes of heavy clay. It is here that year after year the flood waters spread the finer river mud over the countryside. Sediments that are washed from the land are eventually carried by the river to the sea, where they fall to the bottom, perhaps to be raised millions of years hence to form dry land again. The formation of soil from the sands, the silts, and the clays brought down by the rivers and dropped into the sea is a process which can be followed in any large estuary. Soil building on a salt marsh begins as far out as the lowest ebb tide levels, where the foreshore is covered for some time every day of the year. Here, various algae grow on the surface and help to bind the shifting mud against the motion of the waves. This slightly firmer support can then be colonized by plants of the glasswort, Salicornia. This is a fleshy plant able to grow in very salt water. With its rigid, upstanding stems and firm roots, it further hinders the scouring waves, and silt is deposited, thus raising the level of the marsh. In some places, the process is helped by the rice grass, Spartina, which forms dense clumps well out on the mud flats, joining together in large stretches towards the shore. Eventually, the level of the marsh is raised above the reach of all but the spring tides. Many of the pools may dry out completely. On this almost dry land, other plants can establish themselves, holding the silt and mud yet more securely. The sea aster, and with it many grasses, are among the first to appear. Another, the sea lavender, covers the marsh with misty blue flowers. The thrift or sea pink is strongly rooted, and its holding power may result in the formation of low hummocks and extensive flat areas between which the tide scours out deep channels. The level of the marsh rises until it is seldom if ever flooded and land plants can become established. Here the sea plantain may be seen. Or, where the soil is more sandy, the sea couchgrass. Salt marsh soil, built up from successive layers of silt and mud and the annual decay of plants, differs greatly from soils developed on dry land. The layering of the material shows distinctly, and the color differences due to the presence of sulfides and other chemicals are clearly seen. When we dig a pit in a well-developed marshland soil, we can see its profile. The finely divided rock materials are mixed with much organic matter from the decayed remains of successive generations of plants. Below, signs of poor aeration and a characteristic prismatic structure are evident. The depth of soil varies from 15 to 30 inches down to the raw silt. Reclamation of marshland soil may take from 2 to 10 years before it becomes safe for cropping. But in the course of time, these soils become highly productive. If cropped too soon, however, the crop may fail because the land is too salty. In the region of the Wash, a vast extent of the finest arable land has been reclaimed from the sea since Roman times. An urgent farming problem is how to make productive the so-called marginal land, which borders mountain and moorland areas. There are vast tracts of this type of country shown here in yellow, particularly in the western and northern parts of Britain. The soil in such places comes from the bare rock, and it may take hundreds of years for it to build up on the harder rock formations. It is a continuous process, but its story can be followed in any mountain district. Even on bare rocks in high places, we can find plants, the lichens, which are well fitted to survive in the harshest situations with a lack of water and nitrogen and subjected to extremes of heat and cold. These are the first agents in the making of soil from bare rock. Mosses come next. Their closely matted, erect stems hold up little pockets of soil in which other small plants can grow. Their roots pierce and rot away the rock, and they also hold the sparse soil more firmly against erosion. After many generations of growth and decay, these little plants gather up enough soil for small shrubs to gain a foothold. The stronger roots of these may penetrate deep into the rock crevices. Later still, there will be soil enough for trees, and the final stage of forest cover can begin. Soil forming has been going on for the 30,000 years since the glaciers of the Ice Age began to melt and their limits retreated northward. Most of the cultivated land in this country was previously under forest. At that period, the British Isles were not islands at all, but a part of the continent of Europe, and much of the land was still covered with ice. The ice melted, and the sea crept south, flooding the vast low-lying plain which is now the North Sea. As the climate grew warmer and drier, trees began to invade Britain from the south. Amongst the first were pine trees, and by 6000 B.C., most of England was covered by dense pine forests. The shade of pine trees is too dense for other trees and shrubs to establish as ground cover. Fungi grow on the smothering carpet of dead needles and develop acidity in the soil, which the barren needles do nothing to correct. So the soil becomes very acid, as we can see by a simple test with a chemical indicator which turns red. Such a soil is called a podzol. In the natural state, it is useless for cultivation. Here is an example of a rye crop failing on a reclaimed acid soil which has been insufficiently limed. Such was the condition of the soil covering most of England up to 5000 B.C. Soon afterwards, the climate began to change to warm and wet, and the pine forest was largely replaced by deciduous oak forest. During this period, the sea rose and covered over the last link with the continent. So we became an island. The Stone Age men were mainly hunters, so the natural course of plant succession and consequently of soil formation flowed on almost without interruption. From about 2500 B.C., after another change in climate, Bronze Age men settled in the uplands and began to clear the forest from the higher ground in the southern part of the country. They were the first of our farmers, and they cleared the forests and started growing cereals and grazing sheep. Later, farming extended into the valleys and onto the lowlands. Cultivation and changes in climate have had their effects, but soil conditions today over much of the country are largely the result of the previous forest cover. Little of this natural vegetation survives today, but there are still small islands of the original oak forest, as for instance the Keskdale oaks in the Lake District. Under a deciduous forest, there is plenty of scrub and ground cover. This forest soil shows a profile divided into several distinct layers. Before discussing the origin of these layers, we must look in more detail at some of the processes at work in soil formation generally. In a moist, temperate climate such as we find today, the soil receives more water as rain than it loses by evaporation. There is therefore a continual downward movement of water in the soil. This we call drainage. Water both carries down with it the smaller soil particles and also removes some of the soluble minerals and organic matter. As this organic matter is largely acid, as in the podzol, other minerals dissolve in the acid water and are washed away. The roots of plants drive down into the soil, often to considerable depths. The total extent of some root systems is said to run into hundreds of miles. The growing root system penetrates the soil in all directions and causes considerable disturbance. And so, soil tilth is influenced by the presence of roots. Apart from this, roots take up moisture and mineral nutrients at every point where they touch the soil. And and they give out carbon dioxide, which combines with water to produce carbonic acid. When a plant dies or sheds its leaves, organic material falls to the surface of the soil. This material is rich in minerals which originally came from the soil. Thus, in nature, there is a cycle of events. The plants remove minerals from the soil for life and growth, and later, when they die, return them. So it is that where there is much vegetation, this cycle of events helps to keep up soil supplies of plant food which would otherwise be leached out by the rain. This is where the enormous population of living things in the soil, both plant and animal, play their part. Earthworms and insects and their larvae may influence the structure and fertility of the soil. But most soil organisms are too small to see, like these nitrogen-fixing bacteria. Bacteria occur in countless millions when soil conditions are favorable. They live by breaking down organic material and converting it into the kinds of food which plants can absorb, the process of decay. The final result is the formation of the blackish substance we call humus, a most important part of soil makeup. Humus improves the tilth of the soil and helps to retain moisture and so prevents the soil from drying out. Some soil organisms injure the plants we grow, like these eelworms, or like this fungus, with its threads spreading through the soil or invading our crop plants. Now that we have seen all these different factors at work, the structure of the brown forest soil becomes easier to explain. The top layer consists almost entirely of dead plant remains. In this particular example, the undecayed grass mat. Below this, the soil becomes a dark brown mixture of loam, organic matter, and humus. The lime and other bases set free from the organic remains by the activity of bacteria and other soil life help to correct the acidity developed during decay. But they can't do it completely, and so the humus layer becomes acid. Underneath the humus layer, the soil is also acid and has less organic matter. It is pale grayish-brown and rather coarse-grained. Most of the minerals have been leached out by the acid waters from above. The finer clay particles are also washed out. A little lodges in the next layer, but most of it in the layer below. This is reddish-brown due to oxides of iron and other minerals. In the lowest layer, aeration is poor, drainage is bad, and the structure is coarse and columnar. Underneath is the material from which the soil was originally formed. The full depth of soil affected by the growth and decay of plants is known as the solum. The depths of the different layers may vary from place to place, but their sequence is constant. Here, the solum consists of 2 inches of leaf and twig litter, 7 inches of dark brown organic loam, 10 inches of paler granular clay loam, 4 inches of darker brown lumpy clay, and 8 inches of reddish-brown heavy clay. Below is the material from which the soil was originally formed. Let us sum up. Slow and complex forces have been continuously at work for millions of years and are still at work forming the soil. First, the great natural forces, then the activities of man. weathering tears apart the rocks. Ice, wind, and water carry away the rubble, grind it down still more, and deposit it elsewhere. Then plant life takes over. In the process of living and dying, and with the help of myriads of other living things, it converts the lifeless rubble and dust of the rocks into dynamic, fertile soil. When man, the cultivator, takes a hand, he alters the balance of nature for good or ill. The soil is a precious thing. Without a knowledge of its makeup and its needs, a man in his brief lifetime can destroy the product of an age-long sequence of events. With the knowledge which science brings, by helping and directing the forces of nature, the farmer can reap a far richer reward and preserve the fertility of the soil for generations to come.